This week we're talking about effect sizes in HLM. And we've talked about this a little bit already with level 2 predictors, but now that we have looked at level 1 predictors and interaction effects, we wanted to loop back and take a closer look at different effect sizes that can incorporate these different ideas. So we now have a comprehensive framework to think about all the components of a two-level hierarchical model, and these include fixed effects for predictors, as well as random slopes and intercepts. We've also discussed other conceptual and computational issues like contextual effects and centering. In doing statistical modeling, our goal is to try to reduce residual variation. So in single level regression, that just means we want to shrink our residual down, so we explain as much of the variability in our outcome as possible. Well, in HLM, it means that we want to shrink both mu0j and epsilon ij. So we want our cluster-specific variability to be shrunk as well as our residual level 1 variability to be shrunk. Level 2 predictors help us reduce mu0j, and level 1 predictors help reduce both mu0j and epsilon ij. This is where the two r-squared subscripts come from. You can think of the t as being w plus b, and then you can think of w plus b as being the epsilon ij and the mu0j from the unconditional version of your model. So in the model that just has random intercepts for the outcome. So we have three sources of variance between, within, and total. So why do we have 12 different versions of r squared? The reason is that there are some different ways of explaining residual variance in HLM in addition to different ways of conceptualizing the actual variance. We're mainly going to be interested in fixed effects. A lot of times we use random effects as a methodological tool to make sure that we can estimate our fixed effects correctly. We may also want to know how much total variability is associated with the variability in our cluster intercepts and slopes. And this is where the random effects are thought of. And this is also the same as the idea behind ICC. So we want to know how much residual variability there is after we think about how much residual variability is associated with the clusters in particular. We could even go a step further in some cases, though. When we do our model estimation, what we're actually doing is producing cluster-specific slopes and intercepts. When we're not actually interested in these cluster-specific slopes and intercepts, what we do is we use them to obtain their averages. So we take the averages of all the cluster-specific parameters, and these are our fixed effects, and then variances of these fixed effects, and these are the random effects. So this is how much the different clusters vary from the fixed effects. However, sometimes these cluster-specific parameters are actually of special interest. And then we can actually treat these random effects as fixed. And that means that we use the actual estimated slopes and intercepts rather than their variances as parameters in our model. For example, if we wanted to fit a model using all schools in a school district, we might be interested in the slopes and intercepts associated with each individual school. So this is why we have so many different r-square values, and the next few slides just demonstrate the keys for what the superscripts and subscripts mean. So these are the superscripts. F1 refers to the level 1 fixed effects. So these are just your level 1 predictors, and they're just the fixed effects at level 1. F2 refers to the level 2 fixed effects. F equals all fixed effects, so F1 and F2. V equals random slope variances, and I tried to highlight the V in variance to link those together to show where it came from. And M equals random intercept variances, or conditional means, and again I tried to highlight the M to show that the M is associated with means. The subscripts are, as we've discussed, between, within, and total. We can also combine F, V, and M like we do with B and W. When we combine B and W, we get T, which is total. But when we combine F, V, and M, instead of creating new letters, we just string them together. So we can make FVM, which would mean that we're accounting for both level 1 and level 2 predictors, the variance in the slopes, and the variance in the intercepts. There are also some combinations that don't make any sense, and they're always going to return missing values in the R squared MLM package because they're just entries of the table that will never ever be populated. For example, R squared F2W. Level 2 predictors can't account for level 1 variability or within cluster variability, so this can never be a sensible value. But because we have a square table when we output the R squared MLM, there is a cell where F2 and W match up, but it's always just going to be NA. This framework is relatively new, and there are all these different R square values, and they're going to have different usefulness depending on the model and the research scenario. And because this is so new, there aren't exactly well-established reporting standards. In fact, when I took this class, it was only 2 years ago, but the paper that this is all based on by Reitz and Sturba came out since that I took that class. So I didn't learn any of this when I took this class. I learned this along with you by speaking with Dr. Chen. So when we're using HLM in practice, we have to think carefully about which R squared values are important for the research scenario. My very general advice is that the most broadly applicable is the R squared FT. So for me, this is the most direct corollary to just regular R squared in single level regression. It's an approximation of what you think R squared might be if your observations were independent, or if you thought you could ignore the cluster membership. So if you were to essentially draw an observation from one cluster at a time and just have one observation from each cluster, this is what the R squared would be. And that you could do in a single level regression because you just have one observation per cluster. It's also the most appropriate R squared if we want to use our model to make predictions on out of sample data, specifically make predictions about clusters that are outside of our sample. So if we fit a model by using 100 different people, and then we want to use our model to make a prediction about what a 101st person might look like, we would want to use the model based on the fixed effects. And so the R squared FT would be the one that would sort of give us a hint as to how much explanatory power our model might have about this next person. Sometimes your variables of interest in particular will be at level 1 with covariates at level 2, or vice versa. Your variables of interest might be at level 2 with covariates at level 1. This is why we also have the F1 and F2 superscripts, because this just lets us think about the two different levels separately. Note that if we only have level 1 predictors, R squared FT is the same thing as F1T, and likewise in a model with level 2 predictors, R squared F is the same as R squared F2. There are also maybe cases where we're really only interested in between cluster effects or within cluster effects, and in this case, we would want to interpret the subscripts B or W instead. We'll talk a little bit more about this in lab together, but you can imagine situations where maybe you're interested in the effects between schools, or you're interested in the effects within persons or something like that. And in those cases, that's where you would use these B and W subscripts as opposed to total subscripts. So Dr. Chen and I actually had a little email discussion about this because I shared my slides with him, and he didn't fully agree with my approach. He did say that it was a sensible approach and that he understood where I was coming from and that it made sense. It just wasn't exactly how he thought about this. So the difference is that my approach treats cluster-specific differences as unexplained, sort of. However, we know that the point of HLM is that there are cluster-specific relationships between predictors and outcomes. For Dr. Chen, if the model has random slopes, the most broadly applicable effect size is actually R squared FVT. And his reasoning is that this also includes the variability explained by the cluster-specific slopes. So, well, we can't use a model that has random slopes to make out-of-sample predictions. We can assume that if we sampled a completely different set of clusters, that the variance around the fixed effects, so the variance in the slopes around the fixed effects, would be similar. The actual individual cluster-specific slopes would be different, but the variance around the fixed effect would be similar. So in a sense, this does more to account for individual or cluster-specific differences, even if we haven't actually explained them with predictor variables. It tells us a little bit about what's happening with our cluster structure and what we can expect even if we resample different clusters. Why don't we include M? And the reason is that M represents random intercepts. And in a random slopes model, or in any model that has level 1 predictors, the random intercepts aren't simple means anymore, but they're conditional means, conditional on how we centered our data. They're what our outcome variable is when all of our predictors are 0 based on whatever centering procedure we used. It's a little bit harder to sort of justify the relevance of the actual estimated random intercepts in a random slopes model, or really any model with level 1 predictors. And this is similar to why we don't interpret the intercept in single level regression. But in theory, you could come up with a research scenario where this might be important, and this is another thing we'll talk about during the exercises in lab. But for the most part, the two most broadly applicable R-squares, as we've discussed, are either R squared F or R squared FV, and the difference is that FV does more to account for the actual cluster variability and the cluster structure of your data, whereas F just looks at the fixed effects and how well the fixed effects explain the outcome. The bottom line with all of this is that there isn't a settled recipe. So it's important to understand what each effect size is telling you and whether it's appropriate for your situation. And this is what we're going to do during the lab exercises this time. We're going to look at some scenarios and think about which effect size would be most appropriate to report, to try to help wrap our head around what the different effect sizes are doing.